Hello guys, this is the beginning of a series on a very complex process that we call integral building. The idea is that sometimes you need to do integrals in order to calculate values like the center of mass of an object or the moment of inertia of an object. And in that case, we want an integral to be done over the space occupied by that object and take aspects like density or shape into consideration. In order to do that, we are going to start with something called the mass differential and how it can be treated to make it into an integrable quantity. I would like for you to pay close attention to the first steps, which are crucial, and then we will move on to applications of this process. Thank you for your attention. So, to begin with this analysis of integral building, we need to discuss what we call the mass differential, which is a way to structure the integrals that we want to perform. In order to do that, we are going to start with the simplest possible object, which is a long, thin rod of total mass m and total length L. This is the most symmetrical object that we are going to work with. Basically, the mass of the object is distributed along one dimension only. And in order to analyze this situation, it is useful to consider a coordinate axis that goes in the direction of the rod. We are going to call that the x-axis. And for this example in particular, we want the origin to be placed at one end, the left end of the rod. Because the length is L, then the x-coordinate of the right end is going to be L, which means that the variable x for the rod is going to vary from 0 to L. Any little piece of mass that we consider, we will use it if it is so small as to be considered a particle. And we are going to call that the mass differential. It includes a very small, infinitesimally small amount of mass, and even though it is so small, it has some length. We are going to say that that length is the differential of position, dx. We shouldn't confuse the differential dx with the actual position from the origin, which is the value of x. So basically, what we are saying is that the distance from the origin is given by x, while the length of the mass differential is dx. And we use this symbology because we want to relate the mass with the position variable. In order to do that, we are going to use the concept of linear density, which is of course the ratio of mass per unit of length, or total mass over total length of the object. Now this linear density has a symbol. It is the Greek letter lambda, and so lambda is equal to m over L. But the key point in this situation is that if the linear density is uniform throughout the object, then this ratio of total mass over total length is exactly the same as the ratio of infinitesimal mass for the differential element over its length dx. Now, if the two ratios are equal, then a little algebra tells you that the mass differential is going to be equal to the ratio m over L times the differential of position dx. And we are going to use this whenever we need to build an integral. All of those cases include integrals where you want to go along all of the objects. So you want to integrate throughout the rod some function that varies depending on what is it that you are actually calculating. It could be the center of mass, or it could be the moment of inertia. But that function is related to the mass differential dm. The important part here is that this differential cannot be integrated. You need to switch it with a spatial dimension like x. So you can actually make this the integral of that same function times the ratio m over L times dx. And because now the variable is x, and you know what is the variation of this x variable from 0 to L, you now have the lower and upper limit for the integral. So this is the integral from 0 to L of the function times this spatial differential. So that's how you switch from mass differential to spatial differential. But there might be some variation in the analysis if you want to have the origin somewhere else. For example, sometimes it is convenient to have the origin at the midpoint or the center of mass or the point of symmetry. Say, for example, that you place the origin at the exact midpoint of your rod. Then, because the length is L, the coordinates for the left and right ends are negative L over 2 and positive L over 2. Any mass differential that you take is still going to be symbolized by the same elements, dm for the mass, dx for the length, and the position, even if it's now measured from a different origin, is still called x. So once again, the distance from the origin is x, but the length is dx. In this case, when you do your integral over the rod of the function times dm, that integral needs to be done from negative L over 2 to positive L over 2 of the function times m over L dx. Finally, it might be convenient for you to have an origin that actually lies outside of the object. For example, let's say that you want an origin that is at distance a from the left end. In that case, the x-coordinate of the left end is a, and because the length of the rod is L, then the right end coordinate is L plus a. And once again, any differential is given by an infinitesimal mass dm, an infinitesimal length dx, but the position is still x. So your distance, which is x, has a minimum value of a and a maximum value of L plus a, and the length is dx. Therefore, when you do the integral over the rod of your function dm, that is equal to the integral from a to L plus a of the function times m over L dx. So that is the method to transform the mass differential dm into a special differential dx.